So now let's talk about some of the actual reactions that happen going back and forth in between these carboxylic acid derivatives and the carboxylic acid itself, and then maybe other reactions that these species have, for example, reduction and Grignard. So remember that coming down this ladder is easy, right? So the acyl chloride can easily go to the carboxylic acid by just adding water. It turns out it can easily go to these as well, just by adding what this group is. To get to the anhydride, the acyl chloride would react with a carboxylic acid. To get to the ester, it would react with an alcohol. And to get to the amide, it would react with an amine. And likewise, the anhydride will get to the ester by reacting with an alcohol, reacting with an amine here for the amide, etc. So getting down the ladder is easy. Getting to the carboxylic acid is easy. It's the going back up that we'll talk about right now. And then the other reaction that's tricky is this one right here, the carboxylic acid and the ester, because they are very similar in energy. We're going to have to use the equilibrium, Le Chatelier's principle, in order to drive the reaction in one direction or the other. And we should note too that the amide is a little bit lower in energy than the carboxylic acid. So again, that might be one that we either have to add heat or trick it. For typical nucleophilic acyl substitution, the general mechanism has two core steps, and that is nucleophilic attack at that carbonyl carbon, and then loss of a leaving group. So depending on whether this is an acid or base, we'll have to throw some proton transfers in around these two core steps. But nucleophilic attack and loss of a leaving group are going to happen in all cases. The nucleophile attacks the carbonyl, we form this tetrahedral intermediate, then the carbonyl reforms and we lose the leaving group. Remember, hydrogen and carbon cannot leave, and so those are going to, like we talked about before, going to do nucleophilic acyl addition, not a substitution. Here's just a sample of how this reaction happens. We have the nucleophilic attack on the carbonyl and we kick up. Here's our tetrahedral intermediate. Then we kick down and kick out the weakest base. And in this case, it's going to be the chlorine. Please note that this is not a concerted reaction. This is not SN2. We do not have nucleophilic attack and direct loss of a leaving group. We have to kick back up onto that oxygen and kick back down and out. So it's a two-step process and it's called acyl substitution instead of just substitution. Under acidic conditions, very rarely are we going to see a negative charge form. And likewise, under basic conditions, very rarely are we going to see a positive charge form. So if we look at specifically acid conditions in the hydrolysis of an ester, we have an ester reacting it with water in the presence of acid to give us the carboxylic acid and then the leaving group, alcohol. So we just have to be very aware of the charges that we have in acidic conditions versus basic conditions and when exactly we're going to utilize that proton transfer to move that proton around so that we can keep the charges as required. So under acid conditions, this first step is going to be always protonation of the carboxylic oxygen to get this intermediate here where we have the positive charge on the oxygen. So protonation is always the first step in acid. The first step will not be nucleophilic attack at the carbonyl carbon and kicking up. We will not have this happen in acid catalyzed conditions. The nucleophile in this case isn't strong enough. So we have protonation first. We get this intermediate right here. And so this carbon is much more electrophilic. We're able to use a neutral nucleophile to make this happen. Here's that step. Nucleophilic attack kicks up, and then we end up with this tetrahedral intermediate. So if you look at this species right here, you see that the nucleophile that we just had attacking is positively charged, whereas the leaving group that we ultimately want to leave here is neutral. So you're going to see that we're going to need to do some proton transfers in order to make this leaving group ready to leave and in order to keep our nucleophile attached. And we'll talk about that detail in a few minutes when we talk about Fisher's esterification and hydrolysis of an ester. So we're going to utilize these proton transfers throughout the mechanism in order to maintain no negative charges and to keep our groups protonated and deprotonated the way that we need in order for the reaction to go forward. Now, under basic conditions, things are a little bit different. Because we have such a strong nucleophile, we do not need to protonate first. So under basic condition, our nucleophile is typically charged, and we're going to have attack of the nucleophile and the carbonyl carbon kick up. Our tetrahedral intermediate looks just like this. And so then that's very easy to kick down and kick out the one that we want to leave. Now, in this case, we're going to use Le Chatelier's principle by pulling off the product or adding extra of the nucleophile. And so we'll be strategic in using Le Chatelier's principle in order to drive this reaction one way or the other. Remember that ester and that carboxylic acid are very close in energy. Typically, acyl chloride reactions are going to happen in basic conditions. So we have water attacking the acyl chloride to get to the carboxylic acid, and that's just nucleophilic attack, loss of a leaving group. And then you see later we do end up having to do a proton transfer because our nucleophile was neutral. So under base, typically we're going to have that nucleophilic attack. We're going to have loss of a leaving group direct, and then a proton transfer at the end. Whereas remember in acid, we needed these additional proton transfers to keep everything going. So we can always use lithium aluminum hydride to reduce these carboxylic acid derivatives. Here's just one example. We have the acyl chloride lithium aluminum hydride followed by treatment with water, brings us all the way to the alcohol, and the mechanism is shown there. If we use this special reagent, which is lithium tri-T-butoxy aluminum hydride. Instead of lithium aluminum hydride, we can stop at the aldehyde. And here is the structure of that species down here. You can see that big bulky groups, also one hydride here that we can use for the reaction. So it's just going to go one step. And this reagent is more selective and reacts with acyl chlorides faster than aldehydes so that the aldehyde can be isolated. Also, Grignard reagent, so we can use acyl chlorides with excess Grignard, and we're going to add 2 of those R groups. And the mechanism is shown there, very similar to what we've talked about before. In this case, what we want to note, though, is that there is a second nucleophilic attack because we're adding 2 different R groups, and that our product is now an alcohol instead of a carbonyl compound because we've done this reaction twice. Another reagent that I want you to be aware of is the Gilman reagent, which is lithium dialkyl cuprate, and it can be used instead of the Grignard. And sometimes this is chosen because we can stop by just adding 1. The Gilman reagent reacts only once with the acyl chloride to form just the ketone, so we can stop at the ketone. So in terms of acyl chloride, here's the summary of reactions. Note that we can very easily go to the ester to the amide, different versions of the amide. We can reduce it and go to the alcohol. We can reduce it and stop it at the aldehyde. We can also use Grignard and get the alcohol this way with 2 R groups added, or we can use the Gilman again and stop at the ketone. And then if we look here, remember we've already learned that we can just add water and pyridine in order to get the acyl chloride to the carboxylic acid. However, to get back up the line, we need to use SOCl2 so we can trick that OH group to leave, giving us the acyl chloride from the carboxylic acid. Now, if we talk about reactions of the acid anhydrides, this will be a little quicker. It's very similar in reactivity to the acyl chloride because just like the Cl minus is a great leaving group because it's a weak base, so is the carboxylate here. That leaving group is decent. And so we will have similar reactivities. So this acetic anhydride can very easily convert an alcohol into an ester and an amine into an amide. Here's a summary of reactions for the anhydride. We can go to the ester here using alcohol. We can go to the different amides using different amines. We can reduce back to the alcohol. We can reduce going just to the aldehyde using the special reagent with the big bulky groups. We can add 2 R groups using Grignard or a single R group using Gilman. So you can see that this is very similar. Now, the carboxylic acid back and forth with the anhydride. So we can just add water and hydrolyze off the anhydride piece, or we can react a carboxylic acid with an acyl chloride itself to get back to the anhydride. Okay, so now here, as promised, let's talk about preparing esters. Fischer esterification takes a carboxylic acid and an alcohol in acid conditions, and then we make the ester. This mechanism uses all the tricks we talked about in terms of proton transfers throughout the mechanism so that we can keep everything moving forward. The first step, as always, is the proton transfer. So we protonate the oxygen of the carbonyl. So we end up with this intermediate here, making that carbon much more electrophilic. So we then have our neutral nucleophile attack the carbonyl and kick up and end up with this tetrahedral intermediate. Again, because our nucleophile is protonated and the thing that we want to leave is not, we're going to have to move some protons around to make this move forward. And again, please note that all of these steps are in equilibrium. So we really are going to have to use Le Chatelier's principle to either pull off the product or add more of the reagent or whatever to push it in this forward direction. Okay, back to the mechanism. So right now our nucleophile is protonated, but our leaving group is not. So we're going to do 2 proton transfers back to back. The conjugate base of the original alcohol is going to pull that proton off. So then that nucleophile becomes neutral as attached. Secondly, we're going to take that proton back, put it onto the leaving group so that the leaving group is ready to leave. So we do these 2 transfers back to back. And then ultimately what happens is that oxygen kicks down and kicks out water. So it gets rid of that carboxylic acid moiety. And then we have to do 1 more proton transfer, right? Because our oxygen up here is still charged and protonated. So we need to remove that proton here. And so then we end up with our ester. So notice that there's no negative charges anywhere in this whole mechanism. Everything's either positive or neutral. Notice that we have this protonated version of the alcohol, the neutral version of the alcohol, right? Neutral version of the alcohol, protonated version, right? Neutral. So you can see that we're going to use that alcohol to do all of our proton transfers. So this is definitely an important reaction. This is definitely an important reaction that you should know for both the knowledge check and the quiz. Wink, wink. Now we can go backwards, right? So we can hydrolyze this ester and bring it back to the carboxylic acid in the same condition. So it's the same reaction, but backwards. We're going to protonate. So now we're going to use water as our nucleophile instead of the alcohol, right? So we're going to go backwards. So we have the oxygen getting protonated, and then we have attack of the nucleophile, and then we have proton transfer, pulling it off of the OH that we want to stay. Proton transfer, putting it back on the thing we want to leave. And then we have loss of a leaving group. So this oxygen is going to kick down, kick out. And then we end up with a final proton transfer to get to our product. So this is the backwards mechanism for the Fischer esterification, hydrolysis of an ester. So if we have an ester and we react it with an amine, we get our amide, just like I talked about earlier, because it's lower on the ladder. We can reduce esters to alcohols. We're just going to use an excess of the lithium aluminum hydride, and the mechanism is shown there. Remember that we're going to need to do 2 equivalents so we can add 2 hydrogens. So if we want to reduce the ester, but we want to stop it at the aldehyde step, right? Because typically it's going to go all the way to the alcohol. We're going to use a special reagent called DIBA. And here's the structure of DIBA right down here. Again, it's those big bulky groups with only 1 hydride available. And so we can stop it at the aldehyde using DIBA. We can use Grignard. Again, we can use excess Grignard. We're going to add 2 groups, very similar to the reaction that we saw with the acyl halide. So amides can easily be made from anything above it on the ladder. Acyl chlorides, anhydrides, esters. If, however, we want to take the amide back to the carboxylic acid, this is a very slow reaction and it requires high temperatures, but we can just use acid and water. We can reduce amides as well using lithium aluminum hydride. We're going to do excess of that. So we can add 2 hydrides to get all the way to the amine. So this kind of summarizes everything of the core for the whole chapter here is carboxylic acids right up here at the top. And then we can get to each of the derivatives here, get back up. Those reactions are summarized there. We can get back and forth between these. And then ultimately lower here, we have the aldehyde and the alcohol and then the amine. So these are also reactions possible from either carboxylic acid or any of these derivatives. Okay, so I hope that this summarizes it nicely and that you are all set in terms of the reactions of carboxylic acids and carboxylic acid derivatives. Good luck.